Lower a simple ring of lead into liquid helium, and a hush descends inside the metal. Electrons that once jostled like commuters at rush hour now pair off 2 by 2 into Cooper pairs. The pairs are not separate passengers, emerge into one grand quantum state, a single wave that fills every corner of the lattice. In that collective whisper, electrical resistance vanishes. Push a current and it loops forever, slowed by nothing, as though the copper atoms had turned to glass. Set a small magnet above the chilled ring, and another wonder appears. Lines of magnetic flux, usually free to thread metal, are expelled outright. The Meissner effect. The magnet hovers, locked in an invisible cushion made by the superconductor's refusal to admit the field. What looks like levitation is simply the new vacuum of the Cooper pair C, asserting its boundary. No magnetic trespassers allowed. Hospitals harness this hush every day. MRI scanners use superconducting coils to summon steady fields so strong. They can coax the spins of hydrogen nuclei into radio-visible choreography, hence revealing tumors, ligaments, the flutter of unborn hearts. Engineers dream further. Citywide power lines, without a watt of loss. Magnetically levitating trains whispering at 600 kilometers per hour. Quantum computers whose fragile bits are shielded by the very silence that banishes resistance. Your takeaway: chill certain metals and their electrons link arms, creating a new vacuum where electricity flows without friction and magnets ride on cushions of excluded field. Proof that changing the ground state can rewrite nature's rulebook. Crack a pencil trace under a microscope and peel away a single sheet. You hold graphene, carbon pared down to 1 atom thickness. Range those atoms in a honeycomb, and the electron field inside reshapes its rules. Charge carriers now behave like massless Dirac fermions, racing across the sheet at 1/3 of light speed, immune to many impurities that would trip ordinary electrons. It is as if a fragment of deep space physics has slipped onto a laboratory slide, because these quasi-particles carry almost no inertia. They barrel through corners without backscattering, letting currents glide with unexpected grace. Apply a magnetic field and their energy levels snap into clean steps. The half-integer quantum Hall effect, confirming that the sheet hosts its own brand of relativistic playground. Engineers are quick to listen. Transparent conductors thinner than a soap bubble promise bendable phone screens. Ultra-fast transistors switch trillions of times per second without heating like silicon. Researchers have even shaped graphene into nanodrums that vibrate with such precision. They can weigh a single virus. Yet the true marvel is conceptual. By rearranging familiar carbon, we summon a vacuum where electrons forget their mass. Classical matter becomes a testbed for high-energy ideas, no particle collider required. The sheet in your tweezers is both material and metaphor, tangible evidence that the laws we learn in cosmic accelerators can emerge by clever geometry alone on the tip of a pencil. Your takeaway: graphene turns everyday carbon into a landscape where electrons sprint like massless light, showing that new geometries can conjure new physical laws right in the palm of your hand. Take 2 flawless sheets of graphene, stack them, and nudge one ever so slightly 1.1 degrees off perfect alignment. This minor twist, thinner than a dragonfly's eyelash, transforms the electronic score beneath. The one-speeding Dirac fermions slow to a crawl. Their energy bands flatten like piano keys laid end to end. In the stillness, interactions that were background chatter grow thunderous. And the material shifts personality at a whisper of gate voltage. First, an insulator that blocks all current, then flick. A superconductor that carries it without loss. Scientists call the craft twisteronics, using geometry as a tuning dial for nature's constants. Just the angle by a fraction of a degree, and you watch a tabletop universe switch genres. From Mott insulator blues to superconducting jazz, the laboratory control is dazzling. Electric fields slide the 2 sheets back and forth in situ, letting researchers paint phase diagrams as artists mix color. Why does the twist matter? The misalignment creates a Moira lattice, kilometers wide on the electron scale, corralling them into standing waves that magnify their mutual push and pull. It is as though a stadium wave slows a sprinting crowd, giving neighbors time to lock arms and attempt new choreography. Practical horizons, sparkle superconductors that work closer to room temperature. Ultra-sensitive strain sensors, quantum bits born of correlated states. But the deeper wonder is philosophical. A gentle rotation of carbon layers rewrites physical law, reminding us that geometry itself can be an author of reality. Your takeaway. A 1-degree twist between graphene sheets births an entirely new rulebook. Proof that the angle of a lattice can orchestrate phases of matter unheard of in untwisted space. Picture a two-dimensional plane of electrons cooled to a hush and swept by a powerful magnetic field. In the interior, motion freezes, like cars marooned in a desert storm. Yet along the perimeter, traffic surges. Electrons zip one way round the border in perfectly disciplined lanes, immune to potholes or roadblocks. This is the quantum Hall effect, a topological marvel where the bulk of the material becomes an insulator, but its edges host friction-free highways. Topology cares not for microscopic bumps, prizes whole shapes such as loops, twists, cuts that cannot be undone without tearing the fabric. In a quantum Hall fluid, the electron C takes on a global twist. And that twist guarantees the edge current much as the rim of a vinyl record guarantees a closed groove. You can dent the surface, sprinkle impurities, even remove atoms. The current skirts every obstacle unruffled. Delve deeper, and the passengers themselves grow strange. In certain fractional quantum Hall states, collective ripples break the electron into anion. Quasi-particles carrying fractions of a charge and dancing to statistics, neither fermionic nor bosonic, braid two anions around each other, and the system remembers the path. Not just the meeting, an intrinsic memory that engineers hope to sculpt into fault-tolerant quantum bits. One can already watch these edge states light up as microwaves trace their loops, or measure an ionic charge in delicate tunneling experiments. Each observation hints that information can ride on topology's robustness, promising electronics that shrugged off disorder as mountains shrugged off raindrops. Your takeaway. In topological materials, the interior may slumber, but edges come alive with indestructible currents and exotic anions. Highways and travelers shaped by geometry rather than chemistry. In a basement lab, awash with ruby-red laser beams, physicists chill a puff of rubidium gas until the atoms move slower than a drifting snowflake. Crisscross the lasers, and they form a standing wave egg crate of light, an optical lattice. Each trough traps a handful of atoms. Dial the laser intensity, and you can make the wells deep or shallow, close or far apart. With knobs and sliders, scientists recreate on a tabletop the intricate Hubbard model that once lived only in chalkboard dreams. Need stronger interactions? Sweep a magnetic field and a Feshbach resonance lets atoms link hands more tightly? Want a charged particle in a magnetic field? Shake the lattice rhythmically, and a neutral atom feels a synthetic Lorentz force, tracing tight cyclotron orbits without a single electron in sight. Within this light-built city, researchers watch superfluids freeze into Mott insulators, measure sound waves racing at record low temperatures, even glimpse analog Hawking radiation as density ripples escape an artificial horizon. Photons themselves can be herded too. Drill microscopic holes in silicon, and you craft a photonic crystal, a landscape where certain colors roam while others are banished. Curve the crystal's pattern, and light behaves as though space has bent. Vary the index, and you give photons a synthetic mass. Recently, waveguides etched in glass coaxed entangled photons to mimic relativistic particles tunneling through potential barriers. Quantum field theory enacted at the speed of light. Here we are no longer mere observers of nature's laws, or composers, scoring new symphonies of forces and particles with laser light, magnetic wands, and lithographic chisels. Your takeaway. Cold atom traps and photonic lattice let scientists build pocket universes. Programmable arenas where forces, masses, and even horizons are dial-a-law creations. Across this chapter, we have seen matter made to levitate, electrons stripped of mass, and edges that host immortal currents. We have twisted carbon into superconductors, braided anions for memory, and used laser light to summon synthetic gravity inside a glass chip. Each experiment whispers the same radical suggestion: physical law is negotiable. Change the vacuum, the geometry, or the interaction pattern, and new fundamentals unfold. That insight now nudges us toward an audacious frontier. If a 1-degree twist can conjure fresh particles, if a standing wave can mimic an event horizon, might space-time itself be an emergent fabric, woven from deeper quantum threads we have yet to glimpse? Theoretical physicists propose that entanglement could knit distance, that wormholes might be entangled pairs writ large. Gravity could arise the way elasticity emerges in a crystal. Collective, inevitable, but not primary. In the episodes ahead, we will step onto that frontier. We will explore how quantum information may be the loom of geometry, how networks of qubits simulate black hole interiors, and why the dark energy stretching galaxies apart could be a clue that our cosmic quilt is still on the needles. So keep the image of the laboratory universe in mind, a cold atom cloud glowing orange in laser light. In that tiny human-made cosmos, we catch a preview of a deeper truth. Reality is not a rigid monument, but an ongoing weave, and we, the curious, have begun to tug at the threads. Your takeaway? The ease with which labs rewrite microscopic law hints that even space-time may be a fabric still being woven. Our next journey shall follow those emerging strands.